Hello all. I'm just going to summarize this lesson over here. Unfortunately, I'm going to miss out on all the cool and awesome anecdotal stories, but I just have to get to the point in this particular episode. Okay. What do we need to know from this episode? For one thing, we talked about this briefly before. You'll notice that an octave mathematically is double the frequency. Okay. So if you have a standing wave that's generated and it looks like this, if you're able to double it like so by placing in your finger right over here on the guitar, let's say, you'll notice that at the second harmonic, it does work or resonate at double the fundamental frequency. So the first one is F naught for the fundamental frequency. The second harmonic is at 2 F naught. It's also known as the first overtone. And 3 F naught, so 3 times the fundamental frequency, which looks like this. That's known as the third harmonic. That's at the second overtone. Okay, so I'm just briefly summarizing something from a lesson from before. What I do want to point out is that whatever harmonic you're at, you'll notice that it works out to the same as the frequency. Okay, so just watch out for that. So this is the first harmonic. The catch is with the overtone. There is no such thing as zeroth overtone. That's called the fundamental frequency. Okay, so the first harmonic is known as the fundamental frequency. Second harmonic, unfortunately, is known as the first overtone. So there's a misalignment in the numbers. So when it comes to test time, pay careful attention. Are you measuring the harmonic or the overtone? Because that will throw off your numbers. Okay, so please watch out for that. What is definitely true is that anytime that you want to represent an octave one higher, the frequency will literally double. I could briefly demonstrate that for you. That's not too difficult. Good old TuneIt is available over here, and you know, I always like carrying some awesome musical instruments with me. I have one right over here. All right, now this piano over here, it's not tuned to C, but let's look at the numbers. Okay, so this do note over here, what is its frequency? Okay, around 250 hertz. Now, if I want to go one octave up, which is all the way up here, again, mathematically, this will be double of whatever frequency it is here. So if it's 250 over here, logically over here, it'll be roughly around 500. Let's check out the numbers. All right, and there you have it. Anytime you go up one octave, your frequency will double. That you do need to know. Okay, so erase this, and this is what you need to know. Okay, if you tune one octave up, you double the frequency. And if you're going one octave down, it's going to be half that frequency. Okay, the text in blue you don't need to worry about. I'll just let you know that just temperament is the best way to sing in a choir. All right, because when you sing using just temperament, everything sounds beautiful, glorious, heavenly, because you won't hear any of that annoying beat frequency in the background. In truth, whenever you play the piano, there is this annoying beat frequency, and it has to do with the way how the piano is tuned. A piano is always tuned using the equal temperament scale. Okay, and the equal temperament scale is based upon this mathematical formula, and that formula is part of your lab, and that's why I need to get through this guy over here. Okay, in summary, if you're curious, equal temperament is one where your piano is always out of tune. In other words, no matter what key you play at, you're always going to hear an annoying beat frequency. They found out that unfortunately, if you tune in just temperament scale, it will only work beautifully at that key and maybe its dominant fifth, and that's it. All right. Aside from that, if you play any other keys, it's going to sound awful because the mathematical ratios don't work out. Believe it or not, in a perfect fifth, the differences between those frequencies do differ by 50%. So in other words, if your C note is at 250 hertz, let's say, then your G note will be at 50% greater than 250, which I shouldn't have chosen that number, but I think it's at 375. Okay, and that's how it would be ideally. However, if you tune it just for that in just temperament, it'll sound nice in that key, but if you shift the key, the numbers will be out of alignment, and you're going to hear this annoying background sound. I do have a YouTube video on it. It's called Equal Temperament versus Just Temperament. If you have a chance to watch it, feel free to do so. And if your ears are calibrated carefully enough, you'll hear that annoying sound in the background. All right, and that's the problem about equal temperament. Anyways, that formula there is what you need for your lab, because this formula can be used to predict what the notes should be. Okay, so F is equal to F naught, which is your reference frequency, times 2 to the power of n over 12. In our North American chromatic scale, or our Western chromatic scale, you'll notice that there are 12 semitones to make a full octave. Okay, so that's why it's n over 12. Anytime you plug a number into there, it's the next semitone up on a musical instrument. So when you do your lab, you'll notice that, for example, if you're on do, then n is equal to 0 because you're at your fundamental note. If you need to play re on a piano, you'll notice that the re note is 2 semitones up. All right, so that's why you have to jump on re with n is equal to 2. With mi, you have to go 1, 2, 3, 4 notes up. So do, re, mi, n is equal to 4. Fa, if you count it, 1, 2, 3, 4, 5, n is equal to 5. Sol, a lot of people think it's just so, but it's sol. All right, and you count it out, it's going to be, I believe, 7. T, n will be equal to, I think, 9. No, I forgot la. Wow. La, and then T is going to be 11, and then do, n is going to be equal to 12. Because 12 over 12 is equal to 1, and 2 to the power of 1 is 2, meaning that you're double your frequency. And that's how the math works out on musical instruments. Okay, so we usually stick with the equal temperament scale because it just mathematically works out okay-ish no matter what key you're playing in. It'll sound all right. There will be an annoying beat frequency in the background, and yeah, it has been calculated out. This is the annoying beat frequency that you'll hear if you tune your piano using the equal temperament scale. And yes, if you're a piano tuner, you're listening for those beat frequencies. All right. So for example, between C and C sharp, they're hearing for this annoying 5 hertz beat because it has to exist in the equal temperament scale. It won't exist in the just temperament scale. Okay. So that's what you're going to be doing for your lab. In your lab, you'll be recreating an instrument, and the instrument will be recreated based upon this formula over here. Okay, more on the instructions of how to do your lab afterwards, but this is the big key idea of what you need to know from this lesson here. Okay, this magical formula here, which works for the equal temperament scale. If you're wondering, do you need to copy it down? Well, if you look at your lab instructions, it's already given these values to you. Now, the reason why it doesn't give you 440 is because that's how a piano's tuned. You're making your own instrument, and I don't know what key you're playing it in. So you'll sub in your own value of F naught based upon what you have at home. Okay, more on that later on. Any other questions before I advance on? Yes, please ask.
Do we need to know like the do, re, mi, fa? Do we need to know that?
It helps because most of us listen and learn the piano that way. And it's just a way of just describing what the notes are, right? Mi, re, do, re, mi is how you play Mary Had a Little Lamb. And that's just how we name it so that no matter what key you play it into, you still say mi, re, do, re, mi, no matter what key. All right. So it's just a generic way of describing the notes. It's also known as solfege if you're curious. All right. That's what it's called. That's the name, solfege scale. Yeah, even your dog agrees. Great. Okay. Okay. Any other questions, guys? Okay. What else do you need to know? You know what? I don't want to rush too far through this. I still want you guys to know how formulas are created. So that's why I'm going to go through this part here. Okay. So it's really a story of how the equation's created, and then you'll see the equations that I'll give to you on a test. Okay. All right. So as we learned from the second day in, we learned that the speed of a wave on a long tension string is equal to the root of tension divided by linear density. Again, linear density is equal to mass over length, if you recall that. Okay. And then the universal wave equation, which we learned a few days afterwards, is V equals F lambda. So if we have a physical tension string, we can apply these two equations to it in order to predict how the string will resonate. One thing to point out is that when the string resonates like this, one thing you'll notice is that it's not a full wavelength. In fact, let me just erase it right now because that's kind of drawn a little too big. Okay, so I'll keep it small like this, right? When it resonates like so, when you pluck a string, you'll notice that the wavelength here is not a full wavelength. It's only half a wavelength. And that's one of the characteristics of musical instruments that are stringed. All right, they only resonate at their value of whatever the length is, lambda is always equal to 2L. Okay, the real wavelength is always double L, or you could also think about it as L is equal to lambda over 2, right? Because this is only half a wavelength from this red dot over here to this red dot over here. So the first thing we're going to do is we're just going to equate the V's together. So F lambda is equal to this guy over here. And what did I do after that? Oh, I divided both sides by lambda. So lambda is dropped down there. The other thing I told you is that since lambda is equal to 2L, I can draw the picture over here one more time. Why not? Okay, and I'll draw the extension over here. You'll see that this antinode over here, this length over here is only just lambda over 2 across, sorry. Okay, it's only lambda over 2 across compared to your L. So since lambda is equal to double the length, we can sub that in and we get this big formula here. This is the formula that's used to predict what frequency a guitar string will resonate at. It's always going to be 1 divided by 2L times the root of tension over mu. Done. One more thing just to talk about with this formula over here. Often we don't use this formula as is. Instead, we're doing something that we covered a few classes ago where we're doing a comparative analysis. We're comparing what's going to happen to the outcome when you change one factor of it. And whenever you're doing any comparative analysis, what you're doing is you're taking the formula and you're going to divide the formula by itself. So F over F is equal to 1 over 2L over the root of Ft over mu. We'll call the ones up above 2, and we'll call the ones down below 1. All right. Now, if every constant remains the same, so L1 is equal to L2, Ft1 is equal to Ft2, and so on and so forth, then you'll find out that your F2 and your F1 will be the same value because everything all divides out to 1. But if anything changes here, that's how you're going to pitch up and pitch down the frequency of your stringed instrument. Okay, and we'll see what I mean by it with this example here. Okay, what is the relationship between the length of the string and the corresponding frequency? The long way of solving it, again, is that you'll have, and I'll just write it here because I'm kind of out of space, F2 over F1 is equal to, and we're just rewriting the formula twice, 1 over 2L over the root of Ft over mu, 2 divided by 1 over 2L root of Ft1 over mu1. Okay, so what's the relationship in length? In other words, let's say you change the length of the string, but you do not alter anything else. In that case, you'll notice that your tension of this string remains the same. Mu remains the same. So in other words, these two values, they'll just cancel out. What are you left with? Well, you're left with F2 over F1 is equal to 1 over 2L2 over 1 over 2L1. That has the same meaning as 1 over 2L2 multiplied by the reciprocal of 2 over L1 over 1. The 2's will divide each other out, and you get L1 over L2. In other words, F2 over F1 is equal to L1 over L2. And this formula will be given to you. So really, I'm just deriving out how the formula in the green box is derived. Let's repeat that again, and that's why I'm going to try to erase what I can and recycle this formula. This time around, all you're trying to alter, actually, you know what? Let's go through a real life example so that you can correlate all these together, okay? Let's just do it all at once. How do you do this? Well, what you can do is you can take a string and then you can cut it shorter and then play the note again to see how it affects it. And you can cut it even shorter to see how you play it without adjusting the tension at all. And that's probably the hardest thing to do because you can imagine you can never play a song if you're taking the string and you're cutting it and then you're retensioning the same value and then plucking it. Then you play the next note where you have to glue the string together and reattach it. That just takes forever. So what's the shortcut? Guitars are the shortcut. The reason why frets exist is that the frets artificially shorten the length of the string, right? If I play the string alone as is, you're letting the entire string resonate, all right? By me placing my finger down somewhere on a fret, I'm not changing the tension of the string. The tension is still defined by the pull over there. That's why you don't press too hard on the fret over here, because if you press too hard, you're going to pitch up by accident because you're increasing the tension of it. Kind of like this. Whenever you're bending a note, you're artificially keeping the strings the same length, but you're increasing the tension, right? We don't want that. We just want to change the length. And this is the quickest way to change the length of the string without cutting the wire. That's how it's done. So that's how this formula works. And another thing I hope you can appreciate here is that it's an inverse correlation. In other words, the shorter the string, the higher the corresponding frequency. Here's a nice long string, about 63 inches long, and here I am reducing the length of the string. There's my song. I'm a guitar hero now. Okay, so when you shorten the length of the string, the frequency will increase. That is a relationship there. The next one is tensioning. So let's go through tension now. Again, you're not changing the length of the string. You're keeping the length exactly the same. You're not changing the thickness of the string or the linear density. That remains the same. So then mathematically, this is what you have so far. F2 over F1 is equal to the root of, I'll just call it T. It's just easier to write out. Okay, T2 over the relationship of T1. In fact, that's the master formula right there. F2 over F1 is equal to the root of T2 over root T1. That's it for the formula. And for you math gurus, yes, this could technically be written as this as well. It does share the same meaning. You could write it as an entire root. Okay? But this is the important thing to know now. The relationship is not linear anymore. Okay? Let me just erase the stuff over here because I know that I had it filled in, the relationship. You'll see that frequency and length are inversely correlated. That's true. Frequency and tension, remember, it's a square root. So it's not a linear correlation. It's a power correlation where the power is less than 1. It's a square root correlation. Oh man, I have everything all animated out. There's the animation. Okay, so F is proportionate to root of tension. And here's where you got to watch out. I'm sure many of you guys have destroyed your top E string or maybe even your B string on your guitar. Anytime you're pitching up on the higher strings or any of the strings whatsoever, if you double the tension, the frequency does not double. If you think about it, if you had your FT originally at 1 and now you have your FT at 2, well, the square root of 1 is equal to 1, but the square root of 2 is equal to 1.414. All right. So in other words, by doubling the tension, you've only increased the frequency by 40%. And that's a danger about tuning these strings, especially the fragile ones in your B note and your E note. All right. Minuscule changes in tension, or sorry, big changes in tension over here result in minuscule changes in frequency increase. It's not a linear correlation. It's a square root. So if you twist this too many times, you'll end up snapping the string. And that's why you got to be careful with those strings there. Okay. Meanwhile, the lower strings, because they have less tension on them and they're a thicker wire, they're a bit more forgiving. But you'll notice you'll be cranking like crazy just for it to increase up by a few semitones. It's not a linear correlation. Okay. Oh, wait. This thing is all animated as well. So, booyah. There you go. Okay. You can either call it T2 over T1 square rooted or FT2 over FT1. I'm fine with either method. So the last one is linear density. Okay. How does that affect it? Remember that linear density is pretty much the wire itself for the string, how thick it is. Okay, and if you take a look at the setup over here, if you leave the length the same, you leave the tension the same, but all you're doing is making the string either thicker or thinner, here's the correlation. Initially, it looks like F2 over F1 is equal to 1 over root mu 2 over 1 over root mu 1. Okay, so you're initially just pretty much dividing a fraction by another fraction. This is equal to 1 over root of mu 2 multiplied by the reciprocal, which is mu 1 over 1. And that's why the final formula looks like that. What I want to point out is that once I erase the green stuff here, is that it's an inverse root correlation between frequency and linear density. Do you need to know how to derive the formulas? No, but I'll show you that. I'll give you these formulas. No big deal. Okay, I'll give you the formulas, but I wanted to share with you that there is a story behind the formulas because that's important to know. That way, when you're tuning your guitar or instrument in the future, you have that in the back of your mind. You know what to watch out for. Don't overtension your strings. You might snap them too easily. If you want it to be shorter, that's what the benefit of frets are in an instrument. Or even if it's fretless, like a violin, it's the same idea as well. Your finger, when you press it against the membrane or whatever that thing is called, I forgot the name. All it does is it artificially shortens the string, so the frequency goes up. Okay, now for our mathematical problem. Okay, let's say that we had a guitar string and it's 63 centimeters long and it vibrates at 82 hertz. Okay. What if you end up changing its length? How does it affect its final frequency? Let me know when you're done jotting this down. Okay. Now, one thing that you might want to do before you continue with this problem here is that you notice that originally it was at 63 centimeters and it drops down to 47 centimeters, right? That's effectively taking a guitar string, going from here to somewhere over here or here. It doesn't matter. Your ears already tell you the answer. When you short the string, the frequency should go up. So that means that your final answer, it should be greater than 82 hertz. Okay, that's something you want to keep in the back of your mind. Your F2 will definitely be greater than 82 hertz, and that's how you know that you've answered the problem correctly. Okay, so that's just in the back of your mind. How would you solve this now? Well, take a look at your givens. Okay, you have an L1 of 63.1 centimeters, and you have an L2 of 47.2 centimeters. Some people are wondering right now, shall I immediately convert this to meters? You'll see why that's not important very soon. F1 is at 82 hertz. And when you look at the formula, we're using this one over here. F2 over F1 is equal to L1 over L2. Okay, in other words, F2 is equal to L1 over L2 times F1. L1 is at 63.1 centimeter. And hey, look at that. L2 is at 47.2 centimeters. They're both in centimeters. And that's the most important thing. As long as the lengths are the same unit, you're good to go. Could you do this in meters? Yeah, you could. You're going to get 0.631 meters divided by 0.472 meters multiplied by the reference frequency of 82 hertz. Okay? No, you don't have to do that. It's not necessary, but you will get to the same answer at the end. Again, we've already hypothesized that our final answer should be higher, so let's see if this math helps us out that way. In fact, I'm going to type it out as 631 divided by 472, because as you can see, the units don't matter. I could do it in millimeters, and I'll still get the same answer. Multiply by 82, and I get 109, and again, I expected the frequency to go up. So 109.6, 3 sig fig, 110 hertz, we call it a day. That's how it's done. For tonight's homework, course pack page 68. Questions 1 through 4. I think I'll stick with 1 through 4. Skip 3. Yeah, skip 3. So 1, 2, 4. And that will be our adventure for today. Could you do the other ones? I think if you are a guitar head, I'd say try it out because you'll have a better appreciation of why musical instruments work the way they do. So if you want to try out questions 5 and 6 so that you can see the physics of how guitars work, I encourage you to try that out. Any other last questions, guys, before we end off? All right, if that's it, then I'll stop the recording and I'll catch you in the next episode. Bye for now.